All right, this is part 3 of equilibrium, Le Chatelier's principle. Now, we've done all the numerical stuff. We've done all the calculations. We've done, determining the equilibrium concentrations of all the reactants and products in an equilibrium. Done all the mathy stuff. Now, when you go on to your next course, organic, or if you go to take this concept, dynamic equilibrium, to your future coursework, you may never calculate a K ever again. A lot of the math in this chapter you may never do again. What you do need to bring forward, though, is your understanding of what equilibrium is and how it works. What does a large K mean? What does a small K mean? That sort of thing. And again, if you do have to do the calculations, well, a little review, you'll be good. Le Chatelier's principle is all about how an equilibrium responds if you try to alter it. Some textbooks say Le Chatelier's principle is all about what happens if you stress an equilibrium. I don't know what a stressed equilibrium looks like, so I prefer to say alter, or try to impose a change. Now, what kinds of changes are we talking about? Well, we can increase the reactant or product concentrations. We can add reactant or product, or we could take some out. You'll see examples of that in lab. We could increase or decrease the pressure. We could squeeze down on it or let up. We could increase or decrease the temperature. And the question is going to be, if I do these things for a particular equilibrium, does it shift left or does it shift right? How does the equilibrium respond? And Le Chatelier's principle is pretty easy. Whatever you do, it tries to do the opposite. An equilibrium will respond to counter any change you impose on it, if it can. That's important. If it can, it will try to undo what you just did. Now, to spell that out, that's pretty much all you have to know. But to be specific, if you increase the reactant or product, it's going to shift to decrease it. And by the way, if you try to decrease it, it's going to try and increase it. If you increase the pressure, now you may ask yourself, how can I increase the pressure? Well, you can decrease the volume. You can squeeze down on it to increase the pressure. It's going to try and decrease the pressure. Now, how could it do such a thing? Well, the answer is it can shift towards whatever side of the equation produces a different number of moles of gas. So if you try to increase the pressure, it's going to try to shift towards the side where it takes up less space, and vice versa. Now, what about temperature? Say it. If I increase the temperature, it's going to decrease the temperature, but how can you really do that? Well, keep in mind that the temperature is actually a measure of the energy in the environment. So if you increase the temperature, if you increase the available energy, it's going to shift in such a way as to use it up. Now we'll do several examples just to see how that plays out. Alright, so here's your first basic example that we'll do together. And we should probably do these in reverse order. I don't know why I have these in this order, but let's start with the last one, which is the basic question. So add C8H18, which is over here. Now just say it. If I add octane, what's the equilibrium going to try and do? It's going to try and decrease octane. So if I add it, it's going to try and use it up. Which way does this equilibrium shift to use up the C8H18? It shifts that way. If the equilibrium shifts backwards, it will use this up as a reactant if it shifts backwards. So I add octane. Le Chatelier says, I want to take it away, shift left. Okay, let's go back up to the top one. Increase pressure. If I increase pressure, equilibrium is going to try and decrease pressure. So which way could this equilibrium shift and actually let some of the pressure off? Well, let's count the moles of gas. On the left, I have 25 moles of gas. On the right, it looks like I have 9 moles of gas. 8 and 1. So, which way could this equilibrium shift to take up less space? If I try to increase the pressure, how can it decrease the pressure? It can do that by shifting to the right. Shifting towards the side that takes up less space will let some of the pressure off. Now, increase temperature. Or if you think about it, increase energy. If I try to increase the available energy, you guessed it, it's going to try and decrease the available energy. Now, how can it do that? Well, look down here at the delta H. I don't care what the number is so much. I care about that sign, which means it is exothermic. And exothermic means it gives off energy. Now, in Chem 1, that's all you had to know. But now this is Chem 2, and we have equilibria. We have reactions that go backwards. So in case there's any doubt, that negative means it is exothermic in, that direction. Going forward, it's exothermic. It gives off energy. But we want to decrease energy. We want to decrease the energy environment. So it's going to run backwards. If it's exo in the forward direction, it is endo in the reverse. So if you increase the available energy, it's going to decrease it by shifting backwards. Now that one's kind of tough to think of that way. There's a lot of little steps there. So I've got an easier way to think about it. I think it's easier. Let's draw ourselves a reaction progress diagram, as we've learned to. So we have energy on this axis. The reaction proceeds this way, and we have reactants and products. Now this was an exothermic reaction. So what that means is the reactants start up here, we go up over the hill and down here. So it's an exothermic reaction. The reactants are up here, and the products are there. So here's another way to think of it. If I increase the available energy, then the reaction mixture will favor the higher energy side, which in this case is the reactants. Shift that way. Done and done. Say it again. If I increase the available energy, what's in the reaction mixture will favor the higher energy side, which in this case are the reactants. Shift left. Done. Go back and check. That's what we got. Shift left. All right. So this one is for you to do. Now, I don't know if it's good teaching to show you a basic example and then give you a tricky one. I'll just lead off by saying that. But that having been said, take several minutes and try to figure out what the equilibrium does if you do each of these things. Go ahead and pause the video for several minutes, and then let it play, and we'll give you the answer. All right. As I kind of hinted at a second ago, there might be a couple tricks in here, so hopefully you were looking for them. All right, so decrease pressure. All right, so we're going to count our moles of gas. We've got 6 on the left, and we've got 6 on the right. So there's no way this equilibrium can really shift to change the pressure. So Let's go put a big X here. No appreciable change. Now, decrease temperature. So we can do it both ways and make sure we get the same answer. So I'm looking at this delta H down here, and I'm seeing a positive number, which means it is endothermic in the forward direction, which means it's exothermic in the reverse direction. So if I decrease temperature, the available energy, it's going to try to increase it. Which way does it do that? By going backwards, by giving off energy. It is exothermic in the reverse direction. Now, let's look at that the other way. Again, we have our reaction progress diagram. And this is an endothermic reaction, which means we start down here with the reactants, up and over, and those are the products. So if we decrease the available energy, it's going to favor the lower side of the reaction progress diagram. Shift that way. If we decrease the available energy, it'll favor the lower energy side. Shift left. Which is the same answer we just got the other way. Remove oxygen. Okay, this one's pretty basic. If we remove oxygen, it's going to try to replace it. It's going to try to increase it. How do we increase oxygen? We shift towards that side. Oxygen's a product. To make more, we shift to the right. And lastly, add, well, that's glucose, C6H12O6. Solid. It's a solid. No change. Remember, equilibrium expressions, the K constant, does not care about solids. All right. So, yeah, a couple tricks in there, but now you see how it works. One more example. Now, I want you to do this example just like I taught you in the past too. But when we're done, I'm going to try to convince you that you may have known the answer by using your gut some other way, and we'll see if I'm lying to you. So take a minute and do this problem. There's an equilibrium there, and by the way, it's not a chemical reaction; it's a physical change, but it's a dynamic equilibrium. So same rules. So pause the video for a minute. Try to figure out which way the equilibrium shifts if you do each of these three changes. Then we'll give you the answers. All right, let's take it by the numbers. Decrease pressure. So we have 0 moles of gas and 1 mole of gas. We have liquid water evaporating to become gaseous water. So if we decrease pressure, it's going to try and increase pressure. So which way can it increase pressure? Shifting to the right to make more gas. Now, if we decrease temperature, again, delta H says this is endothermic. You have to put energy in to evaporate water. It's an endothermic process. And again, remember, it is endothermic in the forward direction, so it gives off energy in the reverse direction. So if I decrease the available energy, it's going to try and increase it. by shifting backwards. Adding water, liquid. Can't fool you. No change. Liquids are not in the equilibrium constant expression. So those are the answers according to Le Chatelier. But earlier I advertised that you might have a gut feeling for what some of these answers are. So let me do my best here to draw a Chem 1 looking flask. Put some water in it. And let's put a stopper in it. So I actually talked about this at the very beginning of the chapter. Equilibria you may have met before and not known it. So there's liquid water. And in that closed vessel, it'll evaporate to form gaseous water. And again, at some point in time, the rate of, give me a second, the rate of evaporation will equal the rate of condensation, and you will get an equilibrium vapor pressure of water up here. So maybe we have some gut sense for how humidity works. Let's take it in the same order as the previous slide. Let's say I somehow pump the water vapor off the top. How will the equilibrium respond? If we decrease the pressure by pumping, and in this case, let's say by pumping the water vapor off the top, it's going to shift right to make more, and that's exactly what happens. The forward reaction rate increases to make more gas. Now, I've actually seen a video where if you pump the air off the top fast enough, you can actually get the surface of the water to freeze because it's extracting so much energy so fast. So if you pump that water vapor off the top, it's going to shift right, in this case up, to make more. Now, what about decreasing temperature? We might have a sense of humidity. When you're outside jogging, when you're more worried about being all sticky and your sweat not evaporating, August or January? And the answer is August. It's kind of bad chemistry to say this, but I'll say it in a way that makes sense at this point. We probably all know that warm air can, quote unquote, hold more water vapor than cold air can. And there's a number of reasons why that's not quite the right thing to say technically, and there are websites devoted to this, but let's just go with it. So you may have a sense, just based on your knowledge of humidity, that if I decrease the temperature, I'm going to drive the water back into the liquid phase. I'm going to shift the equilibrium this way toward the liquid phase. There won't be so much water vapor up here. The equilibrium vapor pressure of water at a lower temperature will be lower, is the correct thing to say. Maybe you have a sense of that. Anyway, the Chatelier gave us the right answer. Shift left, or in this case, shift down. Now, what about adding a little water? Just a little water. Does that affect the equilibrium vapor pressure of water up here? The answer is no. It depends only on temperature. Filling it a little more does not change the amount of water vapor up here. Le Chatelier said it doesn't because it's a pure phase, and that's true. But looking at it this way, it also doesn't. Now, once in a while, I get a student who says, "But John, if you add a little water, we decreased the volume. That's going to increase the pressure." To which I say, "Yeah, shut up. No, it shows you're thinking." Or, "John, how'd you get the water in there without taking the lid off?" "I used a syringe. I used the force." Whatever. Come on, work with me here. It does show that you're thinking, though. That is Le Chatelier's principle, and that is the end of part 3 of equilibrium.